Hey guys, sorry we got cut off. Let's continue on with Generation 3, Person 2. She is phenotypically normal, and she married into the family. We don't have her parents' information, but we see that she has 2 children. Now, because she doesn't have enough children for that 4+ rule, she is going to have an unknown genotype. Now, if we look at her children, however, both of them are phenotypically normal, and none of them have children, but because both of their father is albino, that means that he had to give a recessive allele to each child, and since they are both phenotypically normal, each one is going to be heterozygous. Now, person 3-3, she's phenotypically normal. We can't tell based on her parents what her second allele is because whichever parent gave the dominant allele, the other parent could give either a dominant or a recessive, and we don't know which one, but she has a child that has the disease. So that means that she has to be heterozygous. And the same goes for her husband. Because he married in, we don't have his family's background, but we do know that he is phenotypically normal and his child has the disease, so he will be a heterozygous individual as well. Now, person 3-6 married into or is from the family. We know that they have a dominant allele, but we don't know what the second allele is because we don't know which parent gave the dominant, and that would mask the recessive allele that they could have inherited. Also, they don't have the 4 children, they only have 3 children, so they are unknown. But each of his 3 children are all normal, but because he married an albino woman, each one of his children are going to either be albino if he's heterozygous, or they're going to be normal and they will be heterozygous. And since we know that they are phenotypically normal, that means that they all have to be heterozygous. So here's our next pedigree. This pedigree is for Huntington's disease. So it's also an autosomal disease. I want you to take a minute and draw down on your piece of paper this pedigree. Don't forget to go ahead and label your people's numbers. I'm going to do that right now. If you recall, Huntington's disease is, yes, an autosomal disease, but it is an autosomal dominant disease, which means that solving this problem means interpreting the phenotypes and genotypes a little bit differently than that of the albinism example we had just completed. Every single box and circle that is unshaded is going to be a person who does not have Huntington's disease. Because remember, shaded in boxes and circles mean that you do have the disease. So all unshaded boxes and circles are going to be normal people, which means that phenotypically they aren't going to have the disease. And since it's a dominant trait, the only way you can have a phenotype that doesn't exhibit Huntington's disease is if you are recessive. So that means every person with an unshaded box and circle is going to be homozygous recessive. This is different than what we did with albinism, but it's different because the inheritance of the 2 traits are different. Now, after we've identified all of these unshaded in boxes and circles, we now go ahead and have the little bit of a trickier task of trying to identify every single box and circle that's shaded in. So we'll start with generation 1. This male has Huntington's disease, and the question you want to ask yourself for a dominant trait is, does this person have any children or any parents that don't have that disease? And since he has a son that does not have Huntington's disease, that means he had to pass along one of his recessive alleles. So since he has the disease but also a recessive allele, he is heterozygous. If we look at this gentleman's son, we see that he has the disease. We see that he has a child that doesn't have the disease and a mother that doesn't have the disease. That means that he has to be heterozygous for Huntington's disease as well. Let's look at his wife. His wife has the disease. Okay, she has a father that doesn't have the disease, and she has a child that doesn't have the disease. So that means she also has to be heterozygous for this trait. Now, if we look at both of their sons, they're both classified as unknown because, let's say the dad gave each of them their dominant allele. We don't know which of the alleles the mom gave, and even if we were to say it was a dominant or a second recessive allele, we wouldn't know, because phenotypically we would just know that he has the disease. So each of them, because they're lacking any children that could be normal, they're going to be unknown genotypically. Same thing applies to the mother, the grandmother in generation 1, person 1-4. She is unknown genotypically because we don't have her parents' information, and she doesn't have enough children. She doesn't have that 4+ children, so she is unknown. But her son is going to be heterozygous because he got the dominant allele from mom, had to get the recessive allele from dad. And when we look at his children, they both have the disease, but because his wife doesn't have Huntington's disease, both of his children are going to be heterozygous for it. Now, if you're solving a pedigree that's not for autosomal, you will be solving one that is sex-linked. And so sex-linked pedigrees are a little bit easier because you have to take into account 2 different things phenotypically: the sex of the person and then the inheritance of it, which we know that all sex-linked traits are recessive. So just like when solving autosomal pedigrees, you have to identify your generations and your people. You then are going to, this is a little bit different, you're going to label all the male genotypes. Every single male, you will know their genotype, because remember, males either have the disease or they don't have the disease. There's no in between. And then after you've identified all the male genotypes, then you'll go ahead and identify all the affected female genotypes. After you've done that, you'll go ahead and you'll figure out the remaining female genotypes by analyzing her parents and her offspring. Specifically, you're going to want to look and see if any males in her family, her father or her sons, have the disease or not. And that will give you a good clue at figuring out what her second chromosome is. If you happen to come across a female that either A, doesn't have children, B, married into the family, or doesn't have enough children, right? We still want that 4+ thing going on. That's supposed to be a plus sign. If we can't figure out what her genotype is, she is unknown genotypically, and we write that with a superscript, like an exponent dash. So it tells me that you know that she's phenotypically normal, but we don't know if she's a carrier or if she's homozygous dominant. So let's solve this pedigree. I'm going to give you a minute to to write it down. I'm not going to go ahead and number my people because there's going to be a lot of letters in here and I don't want you getting all jumbled up. But you should definitely leave enough space and write out the numbers for your people.